So first of all, thank you all for joining us on our first SNAPP seminar of this academic year. And we're so honored to have Professor Kevin Jamieson kick off the SNAPP seminar series for us. So before Kevin starts, so let me give a very brief introduction of Kevin's background. So Kevin Jamieson is an associate professor in the School of Computer Science and Engineering at University of Washington. He is a successful alumni and then indeed did his Bachelor's of Science degree from University of Washington, advised by Maya Gupta in 2009. And then he did his master's degree in 2010 from Columbia University, advised by Ray Castro, and his PhD in 2015 from University of Wisconsin-Madison, advised by Robert Nowak, all in EE. And then he returned to University of Washington as a faculty in 2017 after a postdoc in the AMP lab at UC Berkeley, working with Benjamin Recht. So Jamieson's work has been recognized by an SF Career Grant, as well as the Amazon Faculty Research Award. So we're going to start the seminar for Kevin. So Kevin, you have about 45 minutes, and then I will be monitoring the questions from the chat box for you. Okay, so please take away.
Great. Thank you for the invitation and the introduction. And yeah, please do not hesitate to interrupt me if I miss a question. So I'm going to try to hide the controls. Yeah, so thank you again. I'm Kevin. I'm at UW. And today I'm going to talk about exploration. So this talk will be pretty focused on a pretty simple setting of reinforcement learning, of tabular reinforcement learning, which I'll describe in a moment. But what I really want to get at in this talk is, and what really drives a lot of my research is like, what does optimal exploration look like? As researchers, as human beings, we like to learn new skills, how to navigate the world and how to learn new things. What is the best way to actually go about that learning process? And what does optimal exploration actually look like? And so, of course, over the last couple dozen years, we've seen big advancements in RL, practical RL. And a lot of these applications, or all of these applications, are characterized by an insane amount of computation required to train these things. And the reason why it requires so much computation is because the algorithms have to learn a good policy. And this learning a good policy requires actually exploring the environment, trying actions, see what they do. And the current algorithms are just extremely, extremely inefficient. And it really gets you thinking, does there exist better algorithms out there that can make these processes more efficient? And what does that exploration look like? And it also begs the question, what makes an RL problem hard or easy? Are they all the same difficulty? Clearly not. Learning checkers is a lot easier than learning chess. But what are the aspects of those problems that make them easier or hard? So you can imagine looking at a maze. Clearly, the top maze is top maze is harder than the bottom maze to solve this maze. But what is that notion of complexity? And so a lot of previous work, I'm clearly not the first one to ask this question, a lot of previous work has been focusing on somewhat worst case guarantees, but trying to characterize this difficulty in terms of basically the size of the problem instance. So in tabular setting, this may be just counting the number of states and actions, right? And then looking at within all MDPs or environments that have that number of states and actions, how difficult is it to learn a good policy in the worst case environment that's characterized by that size of the problem instance? But what I'm interested in is getting a little bit more fine-grained than that and understanding how do the transition matrices affect the difficulty of learning? How does the reachability of different states affect the learnability of these different MDPs? And so what I really want to do is derive something called instance-dependent bounds. So this is a sample complexity of how many interactions with this environment do I have to make in order to learn a policy that learning time adapts to the specific problem instance. I'll get more specific of what exactly that means in a moment. But again, what I really want to emphasize, you're going to see a lot of complexities in this talk, a lot of complicated expressions, and I don't want you to get caught up on exactly what these expressions mean. They are interpretable, but what I really want you to focus on is what does optimal exploration actually look like? What are the algorithms? What is necessary for an algorithm to do to be optimal? So like I said, we're going to start in a pretty simple setting, episodic reinforcement learning, where you have some agent, there's some environment, some initial state is presented to the agent. The agent returns with some action in response to that state. And then the environment, in response to that action, returns a reward and transports the agent to a new state. Okay, so this new state could be thought of like physics. If I drop a bottle, I know that bottle is going to drop according to physics or some dynamics. But in general, it could just be you're changing to some new state stochastically. And so this process is going to repeat for big H time steps, and then the episode is going to complete. And you will be able to interact with this environment while in the learning phase of many, many episodes. And what we're really trying to do is characterize the number of episodes, the number of these interactions with the environment in order to learn a good policy. And the difficulty here is we assume that the transition matrices, what state is presented given what current state is there and what action you took, that transition matrices are unknown, and also the rewards are unknown. And so what you're trying to do is identify some policy that achieves high reward and expectation. And so a little bit more in math, if it is more convenient, the agent starts with some state, for a little h equals 1 to big H, agent takes some action, agent receives some reward, and then the state evolves to the next state. And okay, and now what we're going to assume is that we have some finite collection of policies under consideration. This could be, if we're in a tabular setting where there's a finite number of states, this could be, all mappings of states to actions, or it could be some subset of policies. These policies could have been engineered by an engineer that knows something about, say, a robotic system or something, and then, but they're parameterized by some hyperparameters, for instance, so it's just some finite collection of policies pi. And now we define the value of a policy to be the expected amount of reward if you rolled out that policy. That means if you fix some policy pi, if every time you're presented with a state, you take an action that is recommended by the policy, because policies are a map from states to actions. And so the v pi is really just the expected amount of reward you would receive if you rolled that policy out for one episode. And we're going to say that there exists some pi star in that finite collection of policies pi that achieves the maximum value. Okay, because there's a finite set, this supremum is achieved. Okay. And the objective here is to find some policy pi hat in the policy set that is within epsilon, has a value achieved within epsilon of the best possible with high probability. Okay, and like I said, we get to interact with this environment over many different episodes. And what we're really trying to do is achieve this goal using as few total episodes of exploration as possible. And so for all those applied RL examples before, this is how many interactions do you have with this simulator that you're playing with to achieve this goal. And we're going to assume that we are not in the generative setting, if you're familiar with this literature, meaning like the agent has to interact with the environment. They cannot just sort of put the system in any state that they want. They have to navigate the system and the environment as you naturally would. And for simplicity, we're going to assume the tabular setting. So this is a finite number of states and actions. And so to visualize this, you can imagine you can go left or right. You start in this DAG, and maybe you're starting at the boat, and you can go left or right, left or right, left or right. But maybe there's a little bit of wind or something like this, so that if you go left, maybe you stochastically actually go right, and vice versa. And so there's rewards somewhere hidden in this finite set of states, and you're trying to achieve as many rewards as possible, expected reward as possible. Some policy navigating through this DAG. If that helps you visualize. Is the setting clear for everyone? Cool. Okay. So, like I said, we're going to be introducing, we're going to be looking at a lot of complexities to characterize exactly what makes a problem hard or easy. And the first notion that we're going to come across is actually the suboptimality gap. Okay. And so it's actually a complicated object because what it's really saying is if we define VH star of S as this is the value that you would get if you started at time H in state S playing the optimal policy. Okay, that is how much reward you would get if you're playing the optimal policy and you started at state S at time H, little h. That is V star of S. And Q star of SA is basically saying, okay, same thing, but at that time, little h, you're not going to play what the optimal policy suggests. You're going to play some other action A that could be suboptimal. So you're going to deviate away from the optimal policy for just this one time step. And then when you transition to the next state, you are then going to follow the optimal policy again. Okay, so it's basically this gap is measuring what is this like single time step? I'm at this time H in this state S. If I just deviate away from my optimal policy just this one time, how much am I going to cost? How much suboptimality am I going to incur by making just that one little change? And we'll see that this is actually is somewhat fundamental to the sample complexity. Okay, and this will come back. Okay, so how do you find optimal policy? If you had, one of the difficulties of reinforcement learning is that we assume that we do not know the state transition probabilities and the reward. But suppose we did. If we knew what the state transition and reward were, how would we find this optimal policy? And it's actually quite simple. It satisfies the Bellman equations, but it's actually just a very simple dynamic programming exercise in this finite time horizon setting. What you do is you initialize Q star of H. You start at the end of the episode, a big H, and you initialize that with the reward. And then you walk backwards in time, and you define Q star of HSA as being the reward, plus the expected value. So this is if you were in a state S and you played action A, this is the probability of transition to state S prime. And then you're going to play the max over A, the best over A of Q star of H plus 1 as prime A. You can do this because you define this on the last iteration of the for loop. And so this is a recursive algorithm to define this Q star. And if you do this and you define pi star as you go to the argmax over all A at each time H in state S, this will define the optimal policy. It's not hard to show. This is as best as you can possibly do. And so this is great if you knew the transitions and reward, but we don't know them. So what are we going to do? Well, assume that you've somehow interacted with this environment a little bit, right? You played some default policy or you just played randomly. Somehow you went and interacted with this environment and collected some amount of data. With some amount of data, you can define empirical estimates for the empirical reward, empirical state transitions. And this state transition could literally just be the number of times I was in state S and I played action A. How many times did I transition to state S prime? Just an empirical counting measure of how many times I transitioned there. So given these empirical estimates, what I'm going to do, the only reasonable thing to do is just to plug in wherever I saw R and P, I just plug in R hat and P hat respectively. But because these are empirical estimates, this could get you down at a bad place because you just lose optimal policy. And so what people do, and what this principle of optimism or a bonus-based sort of exploration is, they add a little bit of a bonus here and here to try to account for that uncertainty. Okay, and the idea here is that what you want to choose these bonuses so that this Q bar is always an upper bound on Q star that we were defining before. So if this was Q star, through some simple math, you can show that you can define exactly what conditions are necessary to define this bonus so that it's always an optimistic or upper bound on the optimal Q function. And so to demonstrate why this works, if you just had a multi-arm bandit, so this is the equivalent setting when you have one state and one horizon h equals 1. This is just, there's no state here. Here is you just use play an action, you get a reward. You play an action, you get a reward. That's it. And so in that setting, what this bonus is literally just 1 over the square root number of times you've taken that particular action. And if you're always playing argmax of the empirical reward plus this 1 over root number of actions, you get something like this, where we have here these confidence intervals are just 1 over root number of times you've taken that action, and these black balls are the empirical means. And what we see is that if you keep doing this strategy, then the best arm, the arm that is the highest mean, will start to be pulled 100% of the time, or it leads to that. If you keep playing the strategy, you're eventually always going to be playing actually just the optimal policy, because none of these confidence intervals can go below the best one. And so you never really have to play that best policy over and over and over. And the intuition is exactly the same for the policy case. Now, when you go to multiple states and multiple horizons, or a longer horizon, what it's doing is you're building this uncertainty and you're passing it back to little h equals 1. And so you're basically saying, given some policy, what is my uncertainty? What is the confidence interval of this policy over the h time step horizon? And then I'm going to play the policy that has that biggest upper confidence bound. And the principle is exactly the same. And what will happen is, if you keep doing this, you will eventually converge to playing a policy that is the optimal policy. And so this is a very popular form of exploration, and it's been extremely successful over the last 20 years. In particular, when you have a full policy set, meaning you're considering a set of policies that map from all states to all actions, then this UCB type strategy has been around for a long time and analyzed over the last several years in tighter and tighter ways. There are some minor differences between these algorithms, but they're all roughly doing something like optimism. And just this year at Colt, I believe it was, my colleague Simon Du and his collaborators has finally got the sample complexity down to SAH cubed over epsilon squared, which is known to be a lower bound for this problem. And so there's no lower order terms. This is tight. And so basically, for the minimax sample complexity, for the worst case MDP with S states and A actions and horizon H, this is the optimal sample complexity. But again, there are easier MDPs or harder MDPs. And what does that difference between easy and hard look like? What is an easy instance? And so these kind of instance-dependent guarantees first appeared for regret. So regret, instead of just a pure exploration play, in regret, what you're doing is for k, basically at each time you're going to play some policy pi little k, and the total amount of regret after big K episodes is literally just the difference between how much reward you could have received if you played that optimal policy every single time, minus the amount of reward you actually received by playing pi k at each episode, little k. And so there's been a number of works over here. Myself with Max Simchowitz in 2021 had one of the first interpretable sample regret bounds. And basically, they had us a complexity, but it's been improved over the years. We've got a complexity that looks like this. And now I'm going to ignore sort of low order terms for the remainder of this talk. There will be log terms and constants and low order terms that I will be ignoring. These are not small factors, and that's an interesting conversation to have. But we're focusing more on the sort of the coarse, large factors in these sample complexity bounds. But anyways, what we showed was that the regret basically was like log k times this sum over states, actions, and horizons of 1 over this delta HSA that we saw on that slide a few slides back. And so what we immediately see is, this difference between log K and root K is big. And so we can see that an MDP is sort of easy if these gaps, these suboptimality gaps, are large. What does it mean for those gaps to be large? It means that if you deviate away from the optimal policy at all, you really get a much smaller reward. That's the intuition here. These gaps are big. If you ever deviate, you get much less reward. So it's a clear signal that you are deviating away from the optimal policy, and it's pointing you towards that optimal policy. And now, given this intuition that we had with the optimism, that little graphic, that little simulation, is that eventually, the amount of time that you're playing the optimal policy goes to 1 if you keep playing this optimism type strategy. And so if you just randomly sample one of those policies from your history, intuitively, you're going to get, that will yield a good policy. And indeed, this is called the online to batch conversion. And so any regret algorithm can be converted, any regret bound can be converted into a pack result. And by pack, I mean, this is probably approximately correct framework. This is just this is exactly just the amount of sample complexity to get a policy within epsilon with probability of at least 1 minus delta. And the sample complexity is bounded by this 1 over epsilon times this gap. And so again, we see that if these gaps are very large, then you can have a sample complexity that's much less than that 1 over epsilon squared rate. Right? And so already, with just reusing machinery that we know from the regret literature, we can get a sample complexity that is reduced and does improve over this minimax, this worst case 1 over epsilon squared sample complexity. Okay. And so, and so that's exactly what I mean by easy, is that this is the 1 over epsilon squared rate is achieved by the minimax algorithm. And if we have, if the MDP is easy, has these large gaps, then you can beat that 1 over epsilon squared rate. And that's what it means for an MDP to be easy, or a sufficient condition. And this is achieved by an optimal sort of regret minimization algorithm. However, this does not settle the question. So my co-authors and I, my student Andrew and colleague Max, we started thinking about this problem for explicitly just pure exploration. And if we made an algorithm specific for the POC setting, could we do even better? Could we even beat this sample complexity? And it turned out that the answer was yes. So again, you're going to start seeing scary sample complexities like this. I don't want you to focus too much on the exact. I will highlight the differences that I want you to focus on. But for right now, this is just some sample complexity. But the important thing is that it involves this notion of WH pi of S prime A prime. This is the probability that if you run policy pi at time H, you arrive in state S prime and play action A prime. Okay, it's a mouthful, but it's basically, it completely characterizes where this policy goes. It's saying at every time H, where is this policy? What is the density of states that this policy goes to? And the reason why it's a density, it's probabilistic, is because those state transitions could be probabilistic. That's stochastic. Okay, and so what we achieved in this paper, it was a Colt 22 paper, and we achieved this sample complexity. And again, it doesn't really matter what the specifics of this are. What is important is that this bound is always minimax optimal, meaning it's never worse than 1 over epsilon squared. And this bound is never worse than this one either. Okay, so it is, this bound is at least as good as this one above it, but it is provably optimal as epsilon goes to 0. And so if you look at this bound, as epsilon goes to 0, you'll notice that it does not blow up. As long as these gaps are all bounded away from 0, so if there is a unique optimal policy, then this sample complexity is always bounded by a finite number, whereas this upper sample complexity will blow up, right? As epsilon goes to 0, this bound explodes. And so, and you can prove that this is actually provably optimal for that condition when epsilon goes to 0. And so this was a major step forward in understanding the sample complexity. But we still knew that it was pretty loose. But before getting into why it is loose, let's talk about, again, what I want to focus on here is what does exploration look like? And one of the big takeaways of this work was that this proposition where it says, there exists an MDP with S states. So it says to identify an epsilon optimal policy, running a low regret algorithm, any low regret algorithm, so any of those algorithms for minimax, requires at least 1/epsilon, so ignoring the S dependence, requires at least 1/epsilon episodes, whereas this sample complexity is just order 1. So it's independent of epsilon. And so what this says is that there is already an immediate difference between regret minimization algorithms and PAC algorithms, meaning an algorithm that is optimal for identifying or for regret minimization, which are most algorithms in this area, they are necessarily suboptimal for pure exploration. If you just want to find a policy, yes, it is sufficient to find to run a regret minimization algorithm. However, it is provably suboptimal. It can be arbitrarily worse by running a regret minimization algorithm versus an algorithm that is tuned for just pure exploration. Okay, and so this is sort of the first sort of takeaway of this talk is that what does optimal exploration look like? Well, it certainly is not looking like running a regret minimization algorithm. And this is kind of a surprise because we know that in just multi-arm bandits, a optimal regret algorithm is actually still optimal for PAC as well. And so, but when we transition to MDPs, that is not the case. Okay. So shortly after that, this paper. Sorry, was there a question? Oh. So this paper at Colt was for tabular MDPs. And so the next, as we do in this field, as soon as we understand one setting like tabular, we want to understand a future setting like linear MDPs, which is a strict generalization. And so we did that in our NeurIPS paper that same year. But because it's strict generalization, we can look at that sample complexity and talk about what it is in the tabular setting. What does that sample complexity imply? And we get a sample complexity that looks like this. Okay, again, I don't want you to focus too much on what these terms are, but they're different. These two sample complexities are very different. And what's interesting about this, though, is that these 3 sample complexities that you get are coming from 3 extremely different ways of exploring. This first way is optimism, and it starts at the back at the last time horizon and sort of like percolates that uncertainty back to the front and then tries to play an action that has a upper confidence value. This form of exploration is doing action elimination. It's so naive. It's trying to get to every state. And once it gets to that state, it's trying to just remove actions. It's acting as if it's just every state is its own multi-arm bandit. And it's getting to every state and just starting at the end and trying to just remove suboptimal actions and then trying to find the optimal action in each state. It's a very naive algorithm. Well, no, it's a very complicated algorithm, but like it's a very naive strategy to try to win this. Whereas policy elimination directly looks at each policy and tries to find what policy is optimal directly. It's trying to estimate what the value of each policy is. And that's why you see in the denominator here, the actual policy gap. Where you see V star minus V pi. This is actually the suboptimality between by playing policy pi relative to the optimal policy. And if you start proving lower bounds, this is the sample complexity you're going to get things in terms of policy gap, not in terms of the state action gap. And we'll see this in a moment. So with these 3 different forms of exploration, we showed that action, this sample complexity is always better than optimism. But with these 2, which was better, action elimination or policy elimination? And sadly, what we showed was that, unfortunately, there exists 2 MDPs in which one is optimal and the other is not. And so there's sort of a whack-a-mole. There is not one algorithm that is universally good on all MDPs, at least out of these two algorithms, I mean. Okay, so that's a long build-up into what we're doing today. So what we're going to do today is try to close that gap. We're going to try to come up with what does an algorithm look like that is going to actually achieve the best sample complexity around. And what we're going to do is we're going to start with that NeurIPS 2022 paper that was solved for linear MDPs, but I'm going to just be talking about tabular today. And it has this sample complexity. Now, this is kind of a big expression, so I'm going to simplify it just by putting this denominator in with a backslash and then define it as delta phi epsilon as the max of the policy gap and epsilon. Okay, so I'm just going to plug this delta phi in, and we get an expression that looks like this, much shorter. This means the same thing, just trying to condense things because unfortunately it's going to get more complicated. So we have this sample complexity from our NeurIPS 22 paper. And about a year afterwards, Al-Marjani, Shahrazoni, and Kaufman showed a lower bound for this problem, which was previously unknown, especially for the epsilon equals 0 case, that scales like this. Okay, the difference here between this bound and this bound is that whereas this is just looking at the state action visitation probabilities of just policy pi in the numerator, this is looking at the difference between the state action visitations of pi versus pi star. Okay, and so the intuition here is that this quantity is going to be much, much smaller when the policy pi goes to similar states as the optimal policy pi star. Okay, if policy pi is basically acting the same as pi star, this complexity is going to be much, much, much smaller. And so this was known as a lower bound, but they did not argue that we achieved it. It was left as an open question of whether this is even achievable. So it wasn't clear if the upper bound was loose or the lower bound was loose. And what this talk is about, in a long buildup, is basically arguing that this lower bound is almost tight, but not quite there. And so this is joint work with Ariana Rang, Andrew, and Lillian Ratliff, all at UW. Actually, Andrew is now, he graduated last spring, and he's actually at Berkeley now, doing a postdoc. But basically, if you look at what we proved, our sample complexity, this term here, this first term is exactly the lower bound. Okay, that was proven. But then we have this second term. And so the main questions that we're going to try to answer in this talk are this extra term that doesn't exist in the lower bound, is it necessary or is it looseness? And then when is this sample complexity better than this sample complexity that our paper from a couple of years ago achieved? And then what are the new ideas? What are takeaways that we can, in studying this very simple finite horizon tabular MDP, what can we take away from this exploration technique that can be generally useful for more applicable general function approximation in RL? That's a roadmap. Okay, so our first result is that the lower bound, the existing lower bound, is not tight. I'm going to call this term the rewards term, and this second term the transitions term. And our result says that there exists a class of instances such that the rewards term, which is the lower bound, is order 1, and the transitions term, which doesn't appear in the lower bound, is 1 over epsilon, and any algorithm requires order 1 over epsilon. Okay? So in other words, it means that the lower bound only containing this term is unnecessary, is loose. There must have some other term that lower bound is not capturing that must be there. That's not in the lower bound, but does it? But we do have this term that appears in our bound. However, we also showed that if the MDP is a contextual bandit, so if a contextual bandit is a setting where basically you have horizon 1, okay? So you have a random state you're placed in a random state, you take an action, and then like the episode restarts. So there's no sort of like dynamics. And in that setting, the transitions term is actually upper bounded by the rewards term, and therefore our bound, this sample complexity does match the lower bound. Okay, and so what these two results say together is that actually there's a fundamental gap between contextual bandits and reinforcement learning. That in contextual bandits, yes, there's no difference. Our algorithm is optimal for contextual bandits, but for MDPs, there does exist something that is different. That just this term is not enough. You need to have this other term, this transitions term. And for those experts in the room, you might be looking at this transitions term and kind of squinting at it. And if you removed this square, if this square wasn't here, then you might recognize this quantity, this numerator, as exactly the performance difference lemma. Okay? And so if that square wasn't there, this quantity is actually equal to delta pi epsilon. And so you'd get a 1 factor delta pi epsilon on top, and you'd cancel 1. And then this whole term would be low order because it'd be order 1 over epsilon instead of 1 over epsilon squared. That would be great, but that square is real. You can't remove it. And it's unfortunate. I don't know what this quantity is. You don't have any intuition for what this quantity is, unfortunately. But it does appear to be real. And again, I want to emphasize, when is this new sample complexity, this differences term that appear in the lower bound, when is that much, much smaller than the sample complexity we got in our nearest paper? And the answer, and this is one of the big takeaways here, is when it's easier to estimate the difference in value functions versus the value itself. That is, when you have two policies, pi and pi prime, when it is easier to estimate v pi minus v pi prime, that means the difference in those values, when it's easier to estimate that versus v pi and v pi prime separately. And that's sort of the answer here, and we'll go deeper into that in a moment. But we can show, it's not hard to show, that there exists some class of instances such that pi star and pi agree on almost all but one state, meaning so if they agree on all but one state, they're basically the same policy. And this left-hand side can be a factor of s squared smaller than the right-hand side. So you can get a substantial gain in sample complexity by looking at these differences. Here's the instance. It's not particularly insightful. Okay. We're finally getting to the meat at the top. What is the algorithm? That's what we care about. What is this? What is the big idea that allows us to get this improved sample complexity and exploration that we can then take to more general settings? So to describe the algorithm, we actually begin with our NERDS paper. This is Wigmaker and Jamieson 22 paper. We're going to build on top of that algorithm, and all we're really going to do is just replace the estimator. It's this insight that actually just for using the maximum likelihood estimator, which is very popular and very, for good reason, we actually show that is suboptimal. To get this improved sample complexity, you must give a better estimator. But to understand how the algorithm works, let's review how this algorithm works first. That uses the MLE. So what it does is let's first just let's write the value in a particularly interesting way. So the value of a policy pi is, again, just the expected amount of reward that you'd receive if you rolled out that policy for an episode. But that is exactly just if you just look at what probability is this policy going to be in each state in action at each time h, and then so that is just where this policy is going to go, and then you just take that inner product with the rewards in those states and actions at those times. Okay, and so this completely characterizes the density of where the policy actually goes completely characterizes what the value of that policy is going to be. And moreover, this density is easy to compute. You initialize it, the first state, it's very easy to figure out what that is. You'll get what that initial state distribution is on time one. And then you just do the push forward measure of if you're at, if this is your state transition or your state visitation probabilities at time h minus 1, by time h, you're just going to push that measure through your state transition matrices. Okay, so it's a little Markov chain. Of course, we don't know what these probabilities are, these state transitions. And so what we're going to do is we're going to replace them with their empirical quantities. It's an obvious thing. So we're going to collect some amount of data. We're going to get point estimates of our transition matrices p hat, meaning, again, just counting measures. Every time I'm in state SA, how many times do I transition to state S prime? And then just take the empirical average. And once I get those, and so I'm going to build up estimates from our W hat pies. And then I'm going to use an estimator of V hat pi as just the inner product between rewards, this is R hat, and W hat H pi. And once I do that, I'm going to take pi hat MLE, the maximum likelihood estimate, as just the argmax of V hat pi. You can show that this is the MLE. And so this is sort of the traditional way that you would actually find this optimal policy. This is a strange way of writing it. This is not the traditional way that you might have computed it. It's more natural to actually compute it using dynamic programming. Basically, you would plug in these p hats to the dynamic program and then solve the policy that way. This is completely equivalent to doing that, but it's a little bit more convenient for how we're going to do things algorithmically. But the point is that if you have accurately estimated all these v pi's up to tolerance epsilon number 2, then you can be guaranteed that v of pi hat MLE is at least within epsilon of the optimal policy. Okay, so this is just like notation. This is where these WH pi's are coming up. They're just the state action visitation probabilities, and they're critical to this calculation. And so how does the algorithm work, though? You had to explore somehow. And so to visualize this, if we have, n states, and then there's A actions. And so if I'm in this state, I take one of these A actions and I transition to the next state, and so on and so forth. And so how we're going to work is we're going to fix some policy pi in. This is some expiration policy. Don't think too hard about what it is right now. We'll solve for it later. But it is just some sort of it explores everywhere. Maybe it's playing actions randomly. Okay? And what it's going to do is, at first, you're going to play a number of episodes so you can estimate W hat 1 pi. So this is what state in action is the policy pi as that first time instant. And you can show very easily that it's just going to take this number of episodes in order to learn this within tolerance epsilon 1. And where I fix just some epsilon 1. And then once I've learned W hat 1, get some estimate for it, then I'm going to try to estimate W hat 2 at this next state, where once I know where that goes, how do I estimate where it goes the next time? And it turns out that it's not a hard calculation. If you just look at the variance of that estimator, if you're running this pi in, the variance of that is acting exactly like this quantity. And so the number of episodes you're going to need is going to be that over epsilon 1 squared. Okay, it's not too important what these quantities are right now, but the point is that you can do this. And what you're doing here, what I want you to sort of observe here is that this is the complete opposite of dynamic programming. So in dynamic programming, you start at the end, and then you push back the uncertainty, and you push back the reward all the way back. Where is in this policy elimination strategy, what we're doing is actually we're starting at the beginning and then pushing forward the measure of trying to estimate where all these policies go. Because if we can estimate where all the policies go, then we can estimate what those values are going to be. So it's a completely different way of actually trying to identify this optimal policy. And so once we've done this for all, we repeated this for all big H time steps, we're going to compute our estimate of v hat pi. Because we solved it with this epsilon 1, we're going to have this tolerance epsilon 1, and we're just going to remove. Right? We're going to do an elimination style algorithm. We're just going to remove all those policies that were by more than 2 epsilon 1. And then we're going to repeat this process with this reduced set of policies and run with epsilon 2 equals to half of epsilon 1, and repeat that log 1 over epsilon times, and you'll get some guarantee. So that will return epsilon good policy, and it'll get some total sum of places that looks like this. And the tricky thing is actually solving for this pi in, getting this inf out here, so it's the optimal expiration policy. This is a very, very cool trick that Andrew came up with, and it uses basically a Frank Wolf style algorithm that optimizes over the feasible policies, what are actually expiration policies. Because again, we are not in the generative setting. You can't just teleport to some state. You have to actually learn to get to that state, and it can be difficult to get there. But the point here is that if you just ran some expiration policy mu, if you did a quick calculation using Bernstein's, you're going to see that the deviation of v hat pi minus v pi is scaling like this quantity here. And this is exactly where this sample complexity comes from. Okay. And it directly gets this sample complexity. Okay. Again, that's sort of like all built up just to say, well, what do we change? What changes now to improve upon this sample complexity? And it's the same algorithm, basically, but the only difference now is that we're going to use a different estimator. And the key idea is that it is easier to estimate the difference in where a policy goes relative to some policy pi prime or pi bar. So if you have some policy pi bar that's acting as a reference, just estimating where your policy goes relative to pi bar is a lot easier. It's a much, much smaller variance than trying to estimate where every policy pi goes at the same time. And we'll hopefully see that in some math. And so what we're going to try to do is actually try to, instead of trying to estimate v pi directly, we're going to estimate d pi, where d pi is defined as the difference between v pi and v pi bar. So we're trying to estimate the relative performance of pi relative to pi bar. And the actual expression for this is given here. It's complicated. You can verify that this is correct. But it's given in terms of this delta pi, which is the difference between the state action visitation probabilities or state visitation probability of pi and pi bar. And like w pi, this can also be computed recursively. So you start with 0 because they're all the same. And then you build it up over time. Again, that feed forward, or push forward measure of the state transitions. And you're going to get, you can update these delta pi's. And of course, we don't know what these state transitions are. So we plug in our empirical estimates for this d hat pi. And then we define this pi hat VR, variance reduced, as just the argmax d hat pi. And the point is that if you compute the variance of this d hat pi, if you rolled out this strategy with some expiration policy mu, if you compute the variance of this guy, or just look at the sample complexity of this guy, or the variant, well, the deviation of this guy, and apply Bernstein's inequality, what you find is that now the variant, or this term, is now dependent on the difference between w pi and w pi bar versus just w pi as we had in the last slide. And so what we're doing is we're trying to, that you get this variance reduction by only estimating where you go relative to pi bar, you get this much smaller sample complexity, or this much smaller variance in this first term. But you get that at the cost of this second term. And again, this second term is hard to interpret. It's not exactly clear what it's doing. But we can show in many cases that it's very, very small. And then we end with, by optimizing over the different things, we get this sample complexity. So the big deal here, the big difference is that by estimating the differences of where these policies go, if you're just trying to estimate the values of the policies pi directly, that has a variance that acts like the variance of w hat pi. But if you're trying to estimate just the differences, the relative performance of each policy, that has a variance that scales with just the variance of these delta hats, which is the difference versus the same thing. And this makes sense. Okay, so if every policy is very, very close to pi bar, then what you're really doing is if you have, if you just wanted to estimate the value of one pi, so any one policy pi, the best thing you could do is just roll out that policy multiple times, right? That's the optimal thing. It's just a parametric rate. It's going to, if you want to get this within epsilon, you need 1 over epsilon squared episodes. That's inevitable if you just want to estimate a v hat. But if you just wanted to get d hat pi minus d pi to be less than epsilon, there are many cases in which this requires only 1 over epsilon episodes. And so this is the big observation, is that you don't need to estimate the value. You just need to estimate the relative value to some reference policy. And so the algorithm is simple-ish. You're going to again do this sort of elimination style algorithm, and you're just using pure quantities everywhere, right? What else are you going to do? You have initial estimates for q hat and w hat. You're going to find some reference policy that minimizes this expression. You're going to find some expiration policy that minimizes this expression. You're going to roll out these two policies to estimate w hat pi bar and all these other quantities. And then you're going to compute your d hat pi, and you're going to remove those policies pi for which they look substantially worse. And you're just going to repeat this. And again, this step is a lot baked into this. This is like a paper in itself, how you actually do this, because you're optimizing over only feasible policies. It's a very cool algorithm, but I'm not going to talk about it here. But this algorithm has a number of limitations. Namely, you have to enumerate the policies, which significantly limits it. And also, you have to reason over, this algorithm critically relies on reasoning over these state action visitation probabilities, which can be like super, super awkward to maintain in, say, continuous state spaces or very structured state spaces. And so this is like the main limitation of bringing this to general function approximation, is actually just trying to computationally maintain where these different policies go and how to do that in a reasonable place. But there are practical algorithms that try to do this. So this is my final slide. So the main takeaway here is that the MLE is not necessarily optimal, but you can replace that by using estimator that's relative to reference policy, because it's easier to estimate the value of the policy relative to something else. And we got an upper bound that's tight for contextual bandits, but has this extra term relative to the lower bound. We've showed this something is necessary relative to the lower bound that is not captured by that lower bound. But we did not show that it is exactly this for all cases. But we do conjecture that this sample complexity, this upper bound, is actually tight. We think that this is actually the right answer, and that there's no other better algorithm out there. But that's just a conjecture. Okay. Well, that's all I wanted to say today. So thank you for your attention, and I'll be happy to take any questions.
Thank you, Kevin, for the great talk. So I have 3 minutes, and then we'll open to the audience to see if there are any lingering questions. Okay, so then I want to ask a question related to one of the limitations that you talked about a couple of slides earlier. So I was just wondering so can some of these computational expensive steps be relegated or delegated to existing black box oracles to expedite the
Yeah. So, yes and no. So, the famous paper, Taming the Monster, for contextual bandits. What they did, they started with an algorithm there for regret minimization, that started with, uh, by enumerating all the policies. And they were able to get away from this enumeration step by doing, a more sort of an argmax oracle style computational primitive. And we also leveraged that in a recent paper for contextual bandits for optimal pure exploration. And so like there's some tools developed there could be useful for this. But we tried a little bit to see if it would extend to this work, and it's a little complicated. Um, it's possible. It's possible that you could just use an argmax oracle and get back these things, um, and remove the restriction that you need to enumerate the policies. I think that's actually very possible. However, the other sort of really awkward thing is maintaining these state action visitation probabilities, these densities, and over continuous state spaces. It just seems really hard. There are some papers out there that have done it, but I just feel like when you start actually lifting up and looking under the hood at these algorithms, they're pretty exploiting nice structures and things of their particular applications. It's hard to avoid just saying that it's Gaussian or something, which might be a very, very big mistake.
Great. Thank you so much for the intuition. Okay,
Hi,
so
Kevin. Thanks for the nice talk. One quick question about the reference policy here. What's the intuition, particularly choosing your referenced policy in this particular way?
Yeah, okay. So the intuition is that you want the reference policy to be intuitively, you want it to be like pi star. You want it to be sort of close to the policies that are still in your set, or in some sense like a center, right? Because this is a variance reduction sort of thing. You're centering your policies around pi bar. And that's why in this step, you're finding the minimization over pi bar relative to all other policies within the remaining set. And so you're really trying to find the center, because like this actually looks like a variance, right? You have this probability and then a squared error. It really is showing as a variance. And then in our sample complexity, what we do is replace that pi bar, that minimization one, with just pi star. It is actually true that you can actually put a min out here. But like, I don't know what that would mean. Like it's a hard thing to think about. But what I do want to emphasize, and I forgot to mention this, so like in many situations, there is a default policy, right? So let's say you are, one of the reasons I started thinking about this problem was some talks on trying to deal with interference, doing A/B testing with interference. And there, that you would have some default policy that was running, that like, let's say you're Airbnb and you're running different A/B tests, they're all interfering with each other because the inventory is different on all the different, if you run A/B tests, like they're going to interfere with each other because they affect the inventory, the state of the system. Okay, so there is some default policy that you have a lot of information on. That would be a really great reference policy because you know a lot about it. You've rolled that default policy out an enormous amount of times. And so if you look at this confidence bound, the K pi bar is the number of times you've rolled out that policy. And that would be, so this term is basically going to be 0. Because if you have some reference policy that you know a lot about, you know exactly what it does, then this second term is just 0. And all you need to do is it's telling you how should you explore relative to this reference policy. And so in different ways, you could write just an off policy paper using this technology that just saying like, well, look, if you have a big baseline, you have a lot of data on, this is telling you exactly how you should explore to get a much variance reduced estimate of how other policies that you're trying to enable, doing A/B testing on these large platforms. This is one of the more promising ways that you can actually use this technology, because the reference policy is just something you've done a lot and is
Thanks.
relatively close.
This is
to-
very nice. Yeah.
I have another vague intuitive question, or
Yeah.
maybe more vague than the others. You mentioned that compared to dynamic programming, this one goes the other way.
Yeah.
Do you have any intuition for why that ends up happening? Is that because of I forget the exact assumptions you were working with, but is it because we're thinking about some set of policies that isn't necessarily all of them, or is it something else?
No, I don't know exactly why. It is different though. It is fundamentally about like how the algorithm thinks and works. It's trying to build up these estimates one at a time, starting at the beginning. And the reason why this is powerful and why I think it's actually fundamental is because you really want to learn where your policies go. In these action elimination and policy elimination algorithms that we've been developing, like they all kind of do this. They need to figure out where the policies go roughly to figure out like, how should I explore? Because if you don't know where the policies are going to go, you don't really know how you should focus your energy in trying to discriminate between those two policies. And so it is optimism, which in dynamic programming, which starts at the end, it like passes that uncertainty back, and it's just a little less. At no point are you actually estimating where the policies go. It's just sort of this very myopic, like, hey, there's a huge glob of uncertainty in the future if we go in this direction. Let's just go in that direction to eliminate it. And it's very much going after estimating the value directly instead of the differences. And it's just very much follow your nose. And that's great for regret minimization. Optimism is really, really great for minimax regret minimization. But as we showed, any regret optimal algorithm is actually going to be provably suboptimal, arbitrarily suboptimal for pure exploration. And it's because of this. It's because it will not, regret minimization is trying to take policies that basically if you take a policy according to optimism, you're either going to get low regret on that episode, or you're going to get high regret and learn something. That's sort of the promise of regret minimization, of these optimism algorithms. You're either going to learn something if you're wrong, or you're going to get high reward. Whereas in pure exploration, a lot of times what you want to do is perhaps take an episode, go to a part of the state space that you're actually going to incur a lot of regret on, but it could be highly informative. And the intuition there is basically saying, hey, maybe if I go to this state, I know it is not an optimal path to the most reward, but if I go to that state, it may gain me easy access to the rest of the MDP. And therefore, I really should do that a lot of the time in order to learn mostly about my environment. And this is like, in a practical sense or an intuitive sense, you think of like playing video games or something. This is the equivalent of like, hey, I know I have to do this sequence of things. Well, I'm just going to jump to each, I'm going to practice on each one of those sequences, those individual things, and die each time. But I'm gaining experience each time, so that when I do have to go in that exact sequence, I've already learned each piece of it. And so that's where a lot of these exploration algorithms are optimal, or give these big advantages, is when they are not just following their nose, trying to accumulate as much reward as possible.
Great, thank you.
Okay, great. So maybe let's give one more round of applause to Kevin for taking the time to speak at SNAPP.
Thank you. Thank you so much for the invitation. I look very much forward to attending these in the future. This is a great series.
Yeah, okay, great. So I we'll all be hoping to see everyone next week. Oh, sorry, on October 28th is our next one.
Bye, all.
Great.
Thank you
Thanks,
so much.
everyone. Thank you, Kevin.